Welcome everyone. On Friday we introduced 2D motion, which is very similar to 1D motion, except for things are moving in 2 dimensions simultaneously at the same time. So, we went through we introduced some of the problem types. Sure, I think it's gonna work. All right, we introduced a couple problem types. Is it a 1D motion or 2D motion problem? And then if it's a 2D motion, then is it a projectile? Projectile motion problem. A projectile motion problem is any time an object moves through 2 dimensions freely through the air. So freely through the air is that idea in the absence of air resistance. So, there's lots of different examples of 2D motion. It could be, the 2 types that we're going to deal with are called horizontal launch or an angled launch. Those are the 2 problem types that we're going to deal with projectile. Because we don't do trig functions in here, we're going to emphasize more the horizontal launch part of it, but we will do some angled launch. So what I have on this stand, that hopefully I have orientated such, is it's kind of like the thing on the Mythbusters video that they showed right at the very beginning. He dropped a marble, and he slow-mo, right, counted how many frames it took to hit the ground, and then he put a ball, and he pulled back the spring, and then he shot it off, right? And then he used how many frames. And I don't remember how many frames difference he was, but he was pretty close. Making up numbers, 3 milliseconds is a pretty small number, right? But then what he did is they kind of kept scaling up and scaling up. So what this is it's the same kind of deal where we can put a ball on this end, which simply pulls the edge, the metal bar out of this side, and then we can put a marble over here, which then should kick one out. Now, it's gonna, like, one should go relatively straight, one's gonna go that way. So we really just gotta listen to hear, like, the impacts and see which one, if there's a difference in time. So we'll listen for impacts.
I heard one.
I heard a difference in impact, yeah.
That didn't work very well.
Hit the cart. Let's try that. Let's try that again. Maybe I should, we'll try without moving anything. If I pull the spring back further, we'll see if that makes any difference. We'll see. Maybe I just gotta move mine. I only heard one that time. All right, let's try this time. Pull the spring back a little bit further. Yeah, that was better. Did you hear 1 or did you hear 2?
Honestly,
You didn't really hear any?
focused on.
If I was going to screw it up again? Alright, I get it. Oh, sorry, I'm going to hit you guys with a tripod on the way through. Sorry.
That's okay.
Kind of, not really sorry, but a little sorry. That's what I'm supposed to say. That's what society says I'm supposed to say, so I said sorry. This, let's try back here. It'll be louder. There. Okay, so let's try it here. If we hit, it'll be louder. If we don't, well. Okay, same time, right? Agreed? 1, to hit. Okay, so this type of launch, this one that went like that, we call that a horizontal because I launched it horizontally, not at some angle. Okay, so we call that horizontal launch because that's what it does. I don't know if I'm going to edit this out. We'll see. We'll see. Okay, so when we talk about horizontal launch, it's object, it's a projectile motion, moving freely through the air in the absence of air resistance, where the only force acting on it is gravity. So if it's a horizontal launch, okay, so let's grab that green sheet out. If it's, oops, turned off my screen. If it's a horizontal launch, that gives us some information. So if it's an horizontal launch, and the way we know that is because the object is it's a horizontal launch, is because we know it's, I have it in quotes on the screen once my screen turns back on. We know it's a horizontal launch because it's, I'm just going to say thrown, but realize it doesn't have to be something that's thrown. Like I didn't throw that marble off the thing in the back, but I could. So it could be a car drives off, I roll a ball off of a table. Lots of different ways we could word these, but the key is it's parallel to the ground. Horizontal means what? Nodding. So it's a horizontal launch problem. We know it's a horizontal launch if the object is thrown horizontal to the ground. And again, I'm using quotes for thrown because it doesn't have to be thrown. It's just really just a nice way to kind of summarize it in one word. The object is thrown. But it could be some other examples of horizontal launch, like wording in the thing would be a ball rolls off the table. A ball is thrown flat. A car drives off of a cliff. Right? Those are all examples of an object like moving, about to go through 2D motion, but not at some angle, horizontal. So we're not going off of a ramp, flying through the air in our car, we're just driving straight off the edge of the cliff. We're not yeah. Okay. But if it's a horizontal launch problem, then you know something. And the thing that you know is that your initial velocity in the y direction is now equal to 0. The fact that a ball rolls off the table, the idea is when a ball rolls off of a table, how fast is it going? How fast is it going this way? Well, it's not. How fast is it going this way? And the idea is initially it's not. It's like a drop problem in the y direction. When we talk about projectile motion or 2D motion, your x column is separate from your y column. Don't mix your x and y stuff. I'll say that a lot. Don't mix your x and y stuff. The only thing that is like kind of in both columns is the time, because remember 2D motion is moving through 2 dimensions simultaneously. It's moving through both the x and the y at the same time. So your times are constant, or the same, but that's it. Okay? So if this ball rolls off of a table, or my hand, and it goes, like we say it's parabolic, but it's just half of the parabola. I actually read an article that it's actually elliptical, not parabolic, but whatever. The idea is that when it leaves my hand, the speed at which it goes this way does not affect the downtime. And that's what that Mythbusters video on Friday was trying to show us. How did they shoot that gun? At some angle or horizontal? Horizontal, right? They used a level, they tried to level it as best that they could, and they fired that bullet horizontally. And as soon as that bullet left the gun, what force is pushing the bullet down range? Kind of a trick question, but not really meant to be a trick question. What's pushing the bullet? Is there a force pushing the bullet that way once it leaves the gun? No. All of the gun burning, pushing happens in the barrel from the powder burn. But once it leaves the barrel, there is no further push downrange. So once it leaves the gun, why does the bullet fall? Because gravity is pulling it down. So the time, and that's right at the end, so we can do that, and we could like match up the frames, and that's what they were trying to avoid, just for the record. Like they did it in the first one where they dropped the ball and they counted how many frames it took to hit, and then they went through and then they launched, and then they counted how many frames it took to hit. But those are two separate videos, and what they wanted to try to do, and that's why they took so much time to try to problem shoot it, is they wanted to have in the exact same video frame both bullets land. Because then it's not, did we sync them upright? Did we get it, the precision, did they leave at the right time? I have two different cameras. Is the frame rate the exact same on both cameras? So that's why they were trying to do all that they did. Now, which bullet hit the ground first? And I'll say this once, and then I'll never say it again. In that video, which bullet hit the ground first? The dropped or the shot? Anybody remember? I'm pretty sure it was the dropped. I think it hit.
Like hit the paper.
I think the bullet
Like it, like,
hit,
slammed the-
and then the next one like, choom, and, but it was really close. You remember the time frames? 39.6, I think. 39 milliseconds. Okay, is what they said. So 39 milliseconds. Milli means times 10 to the third. So it was, the difference was, that's how much difference there was between their two bullets. Okay, so from here on out, when I say which bullet hit first, I'm always going to say they hit at the same time. Now, did they hit it at exactly the same time? The answer is no, there was some difference. But that could be due to timing. They determined that that amount of difference was insignificant enough to finally conclude that they should hit at the same time. And that's like that's why they tested it. It's kind of this classic physics kind of thought experiment, is if they are. So they went through and said it was 0.039 seconds difference. And that's less than like one frame of a movie. Because they said the playback rate of a film is like 24 frames a second. I think is what they said. Okay. So as we kind of work through these, the horizontal launch, the thing that determines the amount of time in a horizontal launch that it takes a bullet fired to hit the ground is not how fast the bullet's shot, but it's how high the bullet is above the ground. Okay? But it's the exact same as if I were to drop it, because which direction is gravity pulling? In the X direction or the Y direction? In only the Y direction. And that's what determines our pull. Okay? So let's go through and let's look at some of these problems. I'm going to kind of go out of order. On the way in, hopefully you grabbed in class 2D motion problems in class. And I want to look at problem number 4. We're going to start with number 4. So in problem number 4, and the reason I'm doing number 4 is a 2D motion problem. But in terms of processes, it's one of the easier ones, just from the standpoint of what we know and what's given. So, we have a woman kicks a rock at 12 meters per second off of a bridge. The stone hits the water 2.4 seconds later. How high is the bridge? How far? What horizontal velocity? Lots of different parts of the question, but let's just start with part A. So a woman kicks a rock off of a bridge at 12 meters per second, and it hits the water 2.4 seconds later. So if we look for numbers, we see that, and we see that. Now I think when we do these problems, I think a quick sketch is going to be beneficial. So I'll do quick sketches because that's about this. The quality of my quick sketch is not a whole lot different than my take a lot of time and effort, and it doesn't give me any additional information. So when we do a problem like that, if we had like a bridge, we have a rock, that's my rock. I don't know why I'm drawing the foot, and what I'm going to, that's not, I was gonna try to kick that rock, I can't draw that. So we're just gonna deal with the rock. We have the rock, and the rock gets kicked off the bridge, and it gets kicked off at 12 meters per second. Now what's gonna happen to this rock? Is the rock gonna go straight down? Is the rock gonna go straight out? No, right? And it's gonna do kind of a combination of the things, and it's gonna do something like that. Okay? So that's what we're kind of given. Now, the first part of this question is how high is the bridge? I'm really saying how tall is it from here to here? Now, we'll get to that. But the rock's going to do something like that, and it's going to land some distance apart. So if we go through and we look at our problem type sheet, yours is green. Is it a 1D motion problem? No, right? It's moving through both the X and the Y simultaneously. So it's a 2D motion problem. So because it's a 2D motion problem, I make a list of two variables. I said that wrong. We make two lists of variables, one for the Y and one for the X. Now, this is a 2D motion problem, which means the amount of time that it's moving in the X direction is the same amount of time that it was moving in the Y direction. They are simultaneous. These two are the same. And that's the only thing that is in both columns. Don't mix your X and Y stuff. Time is the only thing that can go between the two. And they give it to us, we'll get to it in a second. I know. But I'm gonna kind of keep working through that. So it's a 2D motion problem. Is it a projectile motion problem? Is the rock, once kicked and leaving the bridge, is the rock moving freely through the air in both the X and the Y direction? Yeah. Okay, so I'll try to color code this stuff. So it is. So because it says it's a projectile motion problem, then in the X direction, my acceleration is 0 meters per second squared. Because what force is acting on the rock once it leaves the bridge and is kicked off the woman's foot? Nothing. Absence of air resistance. What's true about my velocities if my acceleration is 0? What's true about my initial velocity and my final velocity if my acceleration is 0? They're going to be the same, so I kind of get lazy and I do something like that. Use equation number 3, something to keep in mind when we're looking in the X direction, we should use equation number 3. And the acceleration in the Y direction, it says, according to my little sheet. By the way, I forgot to put an A in here. For some reason I put VY, that should have been an AY. That should be an AY. The acceleration in the Y direction is negative G, which, if we're on Earth, is negative 9.8 meters per second squared. Everything I just wrote in the blue is because it is a projectile motion problem. Everything I wrote in black was because it was a 2D motion problem. Is it a horizontal launch problem? I'll try to do the, I'm going to clarify. I'll try to be consistent with my colors. Green. Is it a horizontal launch problem? Is it thrown horizontal to the ground? Or is it like a ball rolls off a table, a ball is thrown flat, a car drives off of a cliff? Yeah, it is. Okay, now you could say, well, but if I kick something and I get my toe under it, then yeah, that would be an angled launch. But we're not doing that. We're just going to simplify our life. So it's a horizontal launch. My green marker is because it's a horizontal launch, and that tells me my initial velocity of my rock in the Y direction is equal to 0. I haven't talked about angled launch yet, so we're kind of done with this list. Now, last piece is we can pull numbers from our actual question. 12 meters per second, 2.4 seconds. So where does 2.4 seconds go? For which column? Both, good, because it's the same, right? So it took 2.4 seconds to go from here to here in the y direction, and it took 2.4 seconds to go from here to here in the x direction. Okay, so we have 2.4 seconds, and then 12 meters per second. Meters per second is a type of velocity. Now we just got to figure out where. Is it my velocity in the x direction, my final velocity in the y, initial velocity in the x? Well, I don't say that because we already had that filled in. So which one is it? It's our x, right? That's how fast she kicks it off the bridge, and that's 12 meters per second. That's what we can fill in based upon problem types and then information from the problem. So I'll go through my color coding really quick. Everything I wrote in black was because it was 2D motion. 2 columns, my times are going to be the same. Everything I wrote in blue was because we identified it to be a projectile motion problem. We identified it to be a projectile motion problem. Written in green is because it was a horizontal launch, projectile motion, 2D motion problem. And then the red came from the problem. Now we can get to the question being asked. The question, the first part is how high is the bridge? What I'm asking is, what's the delta y? I need a different point. I don't know if orange shows up, but orange is what I'm solving for. Okay? Now, is this question mark in the x column or the y column? So when we choose our equation, we only look at the y column stuff. I only put stuff from the y column in my equation when I try to find something in the y column. Same thing would be true in the x column, but for right now I'm looking in the y column. By the way, we use equation number 3 a lot in this unit. I'm just telling you right now. We use equation number 3 a lot. So, if we look at our equations, and I put the equations on the back side of your green sheet on purpose, just so you have them again for reference. Which equation would we use to solve for delta y? We don't know final velocity, so which one would be the good one? Equation number 3. Good. Whoever said that was very good. Equation number 3 is the problem, or the equation, that we want to use. Now equation number 3 looks a little bit different this time just because we added some of these other subscripts. So it's going to be delta y is equal to VI y times t plus 1/2 AY t squared. And I'm being very purposeful with adding those subscripts that have the y in it, because then hopefully it will help reinforce the idea that I only look at the stuff in the y column. I only use the stuff in the y column for this. So initial velocity in the y direction, because it was a horizontal launch, is 0. This equation kind of simplifies itself nicely, and we can say delta y is equal to 1/2 negative 9.8 times my time, and my time was 2.4 seconds squared. So my delta y is going to equal negative 28.224 meters. Now, let's quick kind of talk about this. What had an initial velocity in the y direction of 0? What was the object that had an initial velocity of 0 in the y direction? A woman kicks off. So the rock was initially moving at 0 meters per second. What it was accelerating down at negative 9.8 meters per second squared? The rock. What fell for 2.4 seconds? The rock. So what was the displacement for the rock? Negative, down, negative 28.22 meters. But the question isn't asking how far did the rock go down. What it's really asking is how high was the bridge. So the bridge is positive 28.22 meters. Right? The bridge isn't negative meters tall. So we just got to make sure we address the question. So we use the rock to determine the height. Okay? How far from the bridge did the rock hit? What variable am I solving for now? How far, here's my bridge. We're trying to figure out how far did it land away. Which variable is that? That's our delta x. So now we can say delta x is equal to question mark. Now is that an x column or a y column? It's an x. So we use equations for the x and only the x column. Now one of the suggestions when we identified it to be a projectile motion problem that has an acceleration of 0 in the y direction is to use equation number, an acceleration of 0 in the x direction. I misspoke. I would recommend that you use equation number 3, but this time equation number 3 is slightly different because its delta x is equal to vix times t plus 1/2 ax t squared. It's still equation number 3, but now I'm talking about the x direction, so I use vix. I use ax to solve for delta x. Once again, equation number 3 simplifies nicely, and that's because in my list of variables, we said, hey, in a projectile motion problem, the acceleration in the x direction is 0, so that whole term, that whole chunk of terms, I guess, cancels out. So delta x is equal to my vix, which we said was the same as my vfx. It's 12 meters per second. Right, we said that was 12. And our time was given to be 2.4 seconds. Our delta x is 28.8 meters. Now this question isn't asked. What happens if she kicked the rock harder? Okay? What if instead of kicking at 12 meters per second, she kicked it at 20 meters per second? Does that change, if this is now a 20, does it, but the height of my bridge is still 28.22 meters tall, does it change the amount of time it takes to hit the ground? If she kicks it harder, will it reach the ground faster, slower, or the same as when she kicked it at 12? Now let's think back to Mythbusters. Bullet dropped versus bullet fired. Which one hit the ground first? Same time, right? The height is what determines the time, not the horizontal velocity. So it hit at the same time. Now, if this is now 12, instead of 12 meters per second, if this is 20 meters per second, if this is now 20 meters per second, will it change how far the bullet goes? Yeah, right? It's going to have more range because it's fired or kicked harder. I don't want to do the rest of these calculations, but let's talk about C really quick. Letter C says, what was the horizontal velocity when the rock hit the water? What I'm asking there is, what is my final velocity in the x direction? Right as it hits the water, how fast is it moving horizontally? The answer is 12, right? Because what force is acting in the x direction? None. So what's true about the velocity in the x direction? It's constant. Okay? Could we, I'm not going to do it, but what would we be solving for if we did part D? What is the vertical velocity when the rock hit the water? In the y direction, right? We'd be solving that last week. And we could, I just don't want to take the time to do it. Sketch the path of the rock. I think I already did. So let's take a look and let's kind of go all the way from the start of a problem. And let's do problem number 1. A tennis ball rolls off of a 0.8 meter high table at 1.2 meters per second. How far from the edge of the table does it land? A tennis ball rolls off of a table that's 0.8 meters tall. How far from the edge does it land? So if we do a quick, what are we looking for, what do we know? It gave us a height, it gave me meters per second, and it's asking for how far. Okay, so that's our problem type. If I were to draw a quick sketch, my quick sketch of a tennis ball rolling off of a table would look something like that. Looks a lot like my last one, right? But the ball is going to be moving in with some speed as it leaves the table, and it's going to hit, and there's going to be some height and some distance. That's what my object's going to do. Now there's some numbers that we might as well put into our picture. Okay, and I think I used it. What does the number 0.8 meters represent? It's a distance, right? Displacement. From where to where? From here to here, choice 1, or from here to here, choice 2? Okay, so from here to here is 0.8 meters. Okay, how far from the edge? Well, now it's saying, well, from here to here is question mark. And it says it leaves the table at 1.2 meters per second. Is that in the x direction or y direction, that velocity? Is that how fast the tennis ball is rolling in the x direction or in the y direction? X, right? So that's going to be there. So now let's work through our problem types. Let's work through our problem types. Is this a 1D or 2D motion problem? Let's start there, 1 or 2D. It's a 2D, right? So because it's 2D, I'm going to use my black marker, I'm going to try to color code this stuff for you. Because it's 2D, I make 2 lists, 2 columns of variables. And because it's a 2D motion problem, the tennis ball is moving through both the X and the Y simultaneously, so my times are going to be the same. So it's a 2D motion problem. Is it a 2D motion problem that's also a projectile motion problem? Is the tennis ball, once it leaves the table, moving freely through the air in both the X and the Y direction simultaneously? Yes, it is. Okay, so because it's a projectile motion problem, blue marker, I can say that my acceleration in the X direction is equal to 0 meters per second squared. And because my acceleration is 0, that means my velocities in the X direction, I X direction only, are going to be the same. They're going to have some value. And because it's moving freely through the air, my acceleration in the y direction is going to be equal to negative g, which on Earth has a value of negative 9.8 meters per second squared. Blue marker, because it was a projectile. Was it, green marker, a horizontal launch problem? Our other choice would be an angled launch. Okay? So if it's a projectile, it's either going to be an angled launch or a horizontal launch. But is it a horizontal launch? Yeah. So green marker, horizontal launch tells me that that is going to be 0. My initial velocity in the y direction is equal to 0. Green marker. Okay? I'm done with my problem type sheet. Now I'm looking for red marker stuff for my problem. And I kind of put some of this stuff on my sheet already, right? In my quick sketch. So where does the 0.8 meters go? Where does the 1.2 meters per second go? Where are my list of variables? Where's the 1.2 meters per second? I heard velocity, I didn't hear the first part of it. Meters per second is a velocity. Is it this velocity or this velocity? Choice 1 or choice 2? Choice 1, right? Is how fast the ball is moving horizontally as it leaves the table. 0.8, what's that? Is that my meters? Meters means it's what? My choices are displacement, velocity, acceleration, or time. It's a displacement. Is that displacement in the x direction or the y direction? Is no. Good, good. Is this ball going up, positive 0.8 meters? Or is the ball going down, negative 0.8 meters? It's going down, so negative 0.8 meters. Okay? My question mark from the problem, and I think that's where I said I was going to go to orange. Where does my orange question mark go? How far does it end? Yeah, so that's my delta x. Our goal is to try to do as little work as possible. Ideally, if I'm looking for the displacement in the x direction, I would go through and solve for displacement in the x direction. And what was the suggestion for an equation in the x direction? If it's a projectile motion problem, ax is equal to 0, vix is equal to vfx, use equation number 3. Okay, so equation number 3. Now I'm going to write this, and it's not going to get us anywhere, so maybe you just want to hold off on it, because I'm going to, well, I'll show you. So ideally we're trying to solve for this, which is in the x direction. So if we go directly to and say, hey, let's try to do as little work as possible, we say this is vi, delta x is equal to vix times t plus 1/2 ax times t squared. And because my acceleration in the x direction was 0, that whole back term cancels out. Delta x, that's what we're solving for. What's our problem though? We don't know time. Okay? We don't know the time yet. And that's a pretty typical thing that's going to happen when we do these problems, is I'll ask you for something in one column, but I'm not nice enough to give you the time like I did in the first one. So what we end up having to do very frequently is we have to solve for time in the opposite column first, and then once we solve for that time, we can then use that time. So we actually got to start in the y column for this particular problem. Okay, so we're going to start in the y column. And if we start in the y column, and we take a look at my variables in the y column, I need to know time. I'm trying to solve for time. So I need to have an equation that does have time in it. But in the y column, I don't know final velocity, and it's not asking me to solve for final velocity. So in the y column, which equation are we going to want to use? We're going to use equation number 3. We use it a lot. Delta y is equal to VIY times t plus 1/2 AY t squared. Very nice equation for us because it's a horizontal launch. That term cancels out. If that term didn't cancel out, we would have both a t and a t squared, which means there'd be 2 solutions for time. Quadratic formula we probably have to use, right? We'll get there. We're not there yet. There's another option besides quadratic, by the way. So now we can plug in our numbers. Negative 0.8 is equal to 1/2 our acceleration in the y direction, which is negative 9.8 times t squared. Negative 0.8 is equal to negative 4.9 t squared. Divide both sides by negative 4.9. We divide by negative 4.9 because it's times t squared. And we're left with a t squared value of 0.16. Now it's not really 0.16, it's 0.16, 3265306, but I'm lazy, I don't want to write all those numbers down. And that's fine because when I do my next mathematical step, which means I have to take the square root of both numbers, once again, I'm lazy, I don't want to type in all those decimal points, so I go the square root of my previous answer, and if you don't know how to do that on your calculator, let me know and I can try to show you if assuming I know how to do it. And we can use every single decimal that that calculator stored, and I can say that my t is equal to 0.404061018 seconds. Okay? So again, I get lazy and I only write 2 decimals. But I'm going to use every decimal that I can when I use that answer. Because if I round that answer now and then I put it into an equation over here, that number gets even more rounded and further from it gets less accurate. So again, now I know my times in both the x and the y direction. And because I know my times in both the x and the y of 0.4 seconds, I can now use that number to solve for the question that's actually asked of how far from the edge did it land. Now, again, me being lazy, I'm only writing 0.4. But in my calculator, I can either store it or because it's just the next math function, I'm going to use every digit that it has. So I'm not going to say 1.2 times 0.4, I'm going to say what that whole thing was, and we get a delta x that's equal to 0.4847, blah, 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 blah. And because that digit's a 4, I can round that to 0.48. So in this case, even if I had used my rounded 0.4, we get that, but we don't want to round that time. And we can store those numbers in our calculator, which makes it nice, because then we can do a different math function in between. Okay? We'll continue tomorrow. Have a good day.